All right, so our last topic is going to be about strain rosettes, and specifically the two kind of most common rectangular and delta rosettes. So, oftentimes you're going to want to align your strain gauges along principal directions, but sometimes, depending on the scenario, if there's, kind of a weld and you're really interested kind of along the weld or where, maybe there's a different coordinate system or rotated coordinate system that you want to kind of apply, or there's just kind of an inconvenience with aligning it essentially along your coordinate system, and instead you have to align your strain gauge like this. You can use a delta rosette or a rectangular rosette. And a strain rosette is basically, it's just a device where you can kind of see it here, where you have multiple strain signals, and then they're arranged at particular directions. Rectangular, all four are 45 degrees apart. Equiangular or a delta rosette, delta, is 60 and then 120, and then they're 60 basically apart from each other. When you take measurements essentially with this rosette, you can kind of see this offset. And so, for example, let's imagine we have a rectangular rosette in a material, and I think it's best to kind of see this as an example. And we have these strains that are measured in microstrain. And let's say we want to calculate the principal strains. You want to calculate let's say you want to calculate the principal strains of your system. So when you're in the principal stress strain as well. So what you're going to do is you want to kind of draw, and this is going to be your strain. This epsilon is essentially your normal strain. This would actually be your shear strain, and it's over 2 because of the difference between the engineering definition and the infinitesimal strain theory definition, but we'll go back to that in a little bit. But let's go back to that example. So we have some strain here that is 72, and what was the other values? 72, 120, and then 248. 72, 120, and 248. Now, these are the strains that are measured. Now, we don't know the normal strains. We don't know what the y-axis value is. So all we know, just like in Moore's circle, we know that a circle will pass through and it'll hit all these different spots. But if I want the principal strains, meaning the strain here and the strain here, or if I want to find what's the maximum shear strain at the top and the bottom here, I have to figure out where these points lie on my circle. And the only way to do that is I have to define the dimensions of my circle. So I have to figure out there's going to be some center of my circle. There's going to be some radius to the circle. And because we're in Moore's circle, or basically Moore's circle space, there's going to be this 2 theta angle relationship between real space. So I have to solve for C, center of my circle, the radius, and this 2 theta value. Well, we can do that because we already know some relationship between where this has to fall, right? So we know these locations, and we can know the relationship, right? So, for example, we know that epsilon A, right, that is going to be equal to C. So if I take the center, this value here will be C times what in terms of the dimensions that we have? So epsilon A is going to be equal to C plus R times cosine of what? Of 2 theta, right? It's just the projection here, right? And this could be minus or plus. Again, there's lots. This will kind of come out effectively in the wash. And it depends on essentially where you're kind of getting reference to. But you'll find essentially that angle. What about B? Well, B would just be C plus R cosine. Now it's 2 theta, but we're in a rectangular rosette, right? So now it is going to be, we have to kind of account for this change in direction here, right? The offset. Because you can pick any initial location direction, right, to start off these equations. There's lots of ways to solve this problem, but once you've established this relationship, this is going to be my first 2 theta, now it has to be in reference. This relationship now has to hold as we're going from here, A to B and then to C. So this will be, it's a 45 degree offset, but it's multiplied by 2, so it'll be this, and then E sub C is equal to C plus R cosine of 2 theta plus 180. And this is how you would solve this problem in a general sense. So let's go ahead and see how it works. So I can solve this. Now I'm definitely going to go to Mathematica. So this is my, and actually there are kind of relationships here that kind of like the plug and chug approach, where we kind of know what those values are, and we'll double check it in just a second, just to make sure that we get our value. And we can kind of see that here. So we'll go back and we'll double check essentially some of these values. So we're going to go here. We're going to assume this is our Young's modulus of the material. So let's go ahead. So we can see here we have our expressions. E sub a equals this. Actually, see what I've done here is I've actually solved it for a different scenario, but let's see if we can get the same answer. We can solve this a little bit better. Actually, let's rewrite it. This is an old notebook. I'm going to say equation 1 equals. So because we know the values, and like sometimes I might want to, I'm just thinking here. So what we're going to do, I'm going to solve it like I'm going to set it up exactly like we solved it there. So 72 times 10 to the minus 6. Actually, why am I not using? Ooh, I see the EAs are flipped here. So I'm going to just say this. E1 is equal to EA set equal to this C plus R times cosine of 2 theta degree. So that's E1. E2 will be this. B now, and then we have to do plus 2 theta degree. I'm going to say plus 90 degree. And then here. Let's do 3. Let's do C. And let's do 180. But you can see the answers don't change. So now I'm going to solve. And I'm going to say E1, E2, and E3. It should give me the values right there. Let me look at this numerically. All right. So you can see that the answers are exactly the same from here. The only thing that's going to change, and we want my center and my radius to be positive because we're going to go out to that largest value. Again, it doesn't matter because you still have the dimensions of the circle. And this is your angle. So that's your theta angle. So it's not your 2 theta, it's your theta. And so now this would be the rotation theta to get into the principal values. So what you're going to do is you're going to do C. Once you have C and R, your principal, let's go ahead and just set it. Center equals this, radius equals this. So for my principal, so my epsilon 1, P strain 1 equals center plus R, P strain 2 equals, and I need to actually type out center plus R, radius. P strain 2 equals center minus R, radius. I can't help myself. And then my shear strain max equals radius. So let's go up here with this plug and chug approach. So the plug and chug approach is saying, let's see, P strain 1. P strain 1 is essentially the same thing here. My P strain 2 is equal to this here. Fantastic. You can calculate out the sigma 1 and all that other good stuff. It's not incredibly important. Max shear would be this. Let's see if we get the angles the same. Angles the same there, and we've got it. So you can kind of see how you can kind of solve those problems. So you're just going to leverage those equations, and you'll find you'll calculate out the values. You can write out your principal strains in this. This is not the most common notation. You do have to understand, like, once you're in the principal strain state. So for example, once I've defined, like, I'm lying on this circle, and really I'm in a state like this because we're looking at plane stress. So once I've established that this exists, we know if there's no strain here and here, there's nothing here, there's nothing here. Is there a stress in the 3-3? if there is a strain, if there's no strain in the 3-3. Now, that's not necessarily the case, but we can basically calculate it essentially from here and here. So your sigma 1 will exist, sigma 2 will exist. So you can calculate that out. And I think you can assume that that's an interesting question. I don't think we can necessarily, I mean, if we're assuming that we're in plane stress, but there could be a strain in the 3-3 here. Actually, not if we're using that, because we have to be in plane stress, excuse me. That must be 0. So, excellent. So, this is how you'll do it. If you do Rosette, it'll be essentially that 60, or the delta. You'll change the angle, or if you get a really weird one, you just change that, but the procedure still remains the same. So, hopefully, good luck on your exams, and then the next time we meet, we'll be getting into the big one, controls. Very, very, very fun, fairly intense lecture, so we'll see you the next time. Thanks. Bye.